If you're going to understand the data that comes from research in astronomy, you need to understand false color images. And if you're going to understand what a false color image is, you need to know about the electromagnetic spectrum. You see, light is an electromagnetic wave, and as such, it has to travel through space. Traveling through space means that it has a certain velocity. It covers a certain distance in a certain time. And for light, that speed is enormous. It's 300 million meters per second. It's the fastest speed in the universe. In fact, the speed limit of the universe, and it's usually abbreviated with a lowercase c. Now, because of the way that waves operate, it's like a series of pulses that follow each other in regular succession. And that means that after one pulse has left, another one will follow it a certain distance behind it. That distance is called a wavelength. Now, depending on how often these pulses are produced, they will have what's called a frequency. That is, how many pulses are created every second. Now, the wavelength is going to be inversely proportional to the frequency, because if you have more pulses more often, they won't be spaced apart very far. So high frequency means low wavelength. However, if you have the spaces very big between them, in other words, a very long wavelength, it means they're not being produced very often. So a long wavelength, a short frequency. Anyway, the various, shall we say, lengths of wavelengths are grouped into categories in what's called the electromagnetic spectrum. Way down at the low end of the electromagnetic spectrum, very low frequency, very long wavelength, we have radio waves. Above those, shorter wavelengths, higher frequencies, we have microwaves. Past that, we come to infrared. And after infrared, we have a little slice of visible light. If you go above visible light, shorter wavelengths, higher frequencies, you enter the ultraviolet range. After ultraviolet, you're going to have X-rays and eventually gamma rays. Because this is a spectrum of frequencies that we can't see, or I should say we can't see most of them, it's often hard to visualize. Literally, they are impossible to visualize because we can't see them with our vision. However, it is possible to try to understand them by analogy. Now, one way that we could do it is shrink the entire electromagnetic spectrum to a tiny sliver of the visible one. So just imagine that you could only see the color green. There are no other colors for you, it's just green. You might as well have black and white vision with a green filter in front of your eye. Only green things appear to have any light coming from them. Anything that is actually red would look black to you because no green light is coming from it. Anything blue would look black to you because you can't see any of the blue light that's coming from it. In that particular case, radio waves, microwaves, and infrared would all be varying degrees of red and orange, with some very, very sensitive eyes being able to see just a tinge of green into the yellower side of orange. On the other hand, things like ultraviolet and X-rays and gamma rays would all be varying shades of violet, blue, and maybe just a little bit of cyan. Well, we have stayed inside of vision, so that picture may not have really served its purpose. So I've got two more for you. One of them has to do with how our eyes work, and another one is one that hopefully I can help you to experience with your ears. So vending machines are features of various public spaces that aren't necessarily available to us anymore. However, when I was a kid, there was a vending machine by a summer camp that I used to go to. And being a kid, I didn't have a lot of money, but I was trying to save up my change to buy a soda in it. When I finally had enough change that I had scrounged together, I was headed for the vending machine ready to make my purchase when an older kid noticed that I had some pennies and informed me that I could not put pennies in a vending machine. I was dumbfounded. They're money. Why can't I put these into a vending machine? Well, I didn't get a soda that day, but I did learn something, that pennies are, well, not created equal when it comes to money that goes into a vending machine. So you can think of it kind of like this. A vending machine is a money acceptor. You can put money into a vending machine. However, it's only designed to handle and accept certain denominations of money. You could give it nickels, dimes, quarters, and dollar bills. Now, there are some vending machines that will accept $5 or even $10 bills, but for the most part, it's as low as a nickel or as high as a dollar bill. Pennies are still money. It's just that as far as the vending machine is concerned, it might as well not be, because it's not able to receive it. In other words, you try to give it a penny, it won't be able to make any sense of it because it's just not designed to be able to accommodate it. Similarly, I can't think of something that could buy more soda at a vending machine than a $100 bill. There's probably only $100 worth of soda in the machine. But if you try to put a $100 bill into a vending machine, it will spit it back out, because for all the vending machine can tell, it's not even money. Light is a lot like that. Your eyes are able to receive light and interpret it, but only certain kinds. Or I should say, only certain wavelengths. Your eyes are able to receive and interpret light that is red, green, and blue. This is the basis of our color vision, and it's also why digital display screens only have red, green, and blue pixels. It's the only lights it needs to make because those are the only lights that we can see. So you can think of red, green, and blue as if they are the nickels, dimes, and quarters that go into the vending machine of your eyes. So a penny would be something like infrared light or microwaves. It is money. It's just that the vending machine won't take it. You could shine an infrared light directly into your eye and you would see nothing. In fact, there are some security cameras that brightly illuminate an area while keeping it in complete darkness. How do they do that? They shine an infrared light on it. That way, our eyes don't see all of the invisible light that's shining on them. They think they're in the dark when actually they're being brightly illuminated. And again, the other way, you can't see the ultraviolet light that's shining all around you from the sun, because as far as your vending machine eyes are concerned, it's all $5 bills that your vending machine eyes won't accept. Okay, well, that's analogy number 2. Analogy number 3 is going to be musical. You see, from red light up to violet light, we're talking about a fairly narrow frequency range. The wavelengths of red light are almost 700 nanometers long, whereas the wavelengths of deep blue and violet light are almost 400 nanometers long. It's in the mid 300s, which means you have approximately from the mid 300s to the high 700s. That's about a range of, the wavelength of red is approximately double the wavelength of violet, is what I'm trying to say. And when it comes to the waves of sound that come out of musical instruments, what we associate with musicality is measured with frequency ratios, which means that in musical terms, you can see 1 octave of light. In other words, red would be a low note in a scale, and violet would be a high note in a scale. But our ears are able to hear many, many octaves of music. In fact, a piano has about 8 octaves in it, I think. Yes, about 8 octaves in it, which means that you could imagine what your eyes see as a limitation of what your ears hear. So this is what a song would sound like with the full spectrum of you being able to hear it. And this is what that same song sounds like if we limit it to just a single octave in the mid-range. Very limiting, isn't it? Well, just as your eyes can't see most of what's going on, in that little example, your ears couldn't hear most of what's going on. So, how can we represent these invisible things so that we can look at them? Well, one thing that we're able to do is build machines that can see them. In other words, put a change machine right next to the vending machine. You can't put a 20 into the vending machine, but you can put it in the change machine. The change machine spits out a whole bunch of quarters, which you can then put in the vending machine. You're just converting something that's too high down into something that's low enough for our eyes to accept. So you could build a camera that only sees X-rays. Take a picture with that camera and then have it represent that image in visible light. It would be kind of like taking a dog whistle too high for us to hear and then just pitching it down until it's something that we can hear. So when you're looking at photographs taken by satellites and various kinds of telescopes for use in astronomy, a lot of those pictures are not actually what the objects look like, because look like means if you could see it with your eyes. These are taken with cameras that can see wavelengths invisible to us. So we may have radio wave telescopes taking pictures of what the radio waves are showing us. We may have infrared telescopes taking pictures in the infrared range, or microwave, or X-rays. Looking through the eyes of these instruments shows us things invisible to our eyes that we're able to translate into something that is visible to our eyes. And various different phenomena in nature are most visible, if you'll pardon the expression, in these invisible ranges. For example, certain phenomena may look one way in visible light, but most of what was really happening was only visible in the ultraviolet. Well, in order to make as informative a graphic as possible, scientists and astronomers will make what are called false color images. And the way that it works is like this. You can take a picture with a radio telescope and take a picture with an X-ray telescope of the same subject, and then just superimpose them on top of each other. Now, are these different pictures of the same thing? Are these different things? Well, it would be kind of like if you took a color picture of something and a black and white picture of it and then just superimpose them. It's just two different cameras seeing different things about the same object. In order to keep the picture sensible, what they will do is they will colorize one of the wavelengths in one color and a different wavelength in another color, so that when they're superimposed, you can see the details from the first picture as separate from the details in the second picture, because you can see where one color shows up and the other doesn't. Not only that, but if you've ever seen an image, say, of a heat map, say an image from a thermal camera, you'll know that you can use color to encode other information into a picture. For example, in a lot of heat maps, red, orange, and yellow, and white refer to very, very high temperatures, whereas green, blue, violet, and black refer to very, very low temperatures. In that way, you are able to use color informatively rather than descriptively about what something looks like. After all, if we're talking about something in the infrared, none of those colors even apply. Anyway, hopefully this is making some sense. Obviously, it's difficult to show you something which by definition you can't see. Hopefully, some of these analogies will work out.